Now, in order to solve second order linear differential equation, our first approach is going to be the method of educated guessing. So, how do we do that? Here is an example. The second derivative of the unknown function equals the unknown function. Well, but you know from the theory of first order differential equation that the exponential function, right, it satisfies this property that its derivative is the same as the function itself. But of course, if you differentiate it again, then it still satisfies this property, and then if you move it to the left hand side, you get 0. So one of solutions is definitely the exponential function. So the function e to the t satisfies this differential equation. Wow. Well, but then what else can we have? Well, let's think. If e to the t has this property that its derivative is the same as the function, what about e to the minus t? Well, let's see. If we have e to the minus t, its derivative is going to be minus e to the minus t. But then its second derivative, when we differentiate second time, then we get minus e to the minus t, which is plus e to the minus t. So it worked again. So the other solution is e to the minus t. But then if you think about it, then you will realize that the sum e to the t plus e to the minus t is also a solution. And the difference e to the t minus e to the minus t is also a solution. And even if you come up with some crazy linear combination, so imagine that we try, say, square root pi times e to the t plus 2018 e to the minus t. This is also a solution. Indeed, if you differentiate it once, then you get square root pi e to the t minus 2018 e to the minus t. If you differentiate it again, then you still get square root pi e to the t, but now you differentiate e to the minus t, you get minus e to the minus t. Minus and minus will give us plus, and this is the same as the original y. So generally speaking, any combination of e to the t and e to the minus t is going to be a solution. So c1 e to the t plus c2 e to the minus t. Well, but combinations of e to the t and e to the minus t, so what we just saw is that each such combination is a solution. But is it true that every solution is a linear combination of e to the t and e to the minus t, or there is something else too? Okay, so here is a more complicated example, but what we are going to do is, well, as we see from first order differential equations and from our simple second order differential equation, is that exponential functions are natural candidates for solutions of linear differential equations. Right, so we are going to try to find solutions in the form e to the power rt. So if this is e to the rt, then y prime is r times e to the rt, and y double prime is r square e to the rt. And now I'm going to substitute y prime and y double prime into the differential equation. So then I'm going to have r squared e to the rt plus 5 r e to the rt minus 24 e to the rt is 0. But now notice that we can multiply this whole equation by e to the minus rt, because e to any power is strictly positive, so it is non-zero. So when we multiply by an equation by a non-zero number, we get an equivalent equation. So we get r squared plus 5r minus 24 is 0. So in other words, what we see is that a function in the form e to the power rt is a solution of this differential equation if and only if r is a solution of the algebraic equation r squared plus 5r minus 24 equals 0. But then this is just a quadratic equation from secondary school that you can learn. So the discriminant is 25 plus 24 times 4. What is 24 times 4 is 94 times 24. Oh, sorry. So it's 96. 25 plus 96, which is 121. Square root of the discriminant is 11. So r, there are two solutions, which are minus 5 plus minus 11 over 2. So minus 5 minus 11 is minus 16 over 2 minus 8. And minus 5 plus 11 is 6 over 2, 3. So minus 8 and 3. Let's check. Minus 8 times 3 is minus 24, correct? Minus 8 plus 3 is minus 5, correct? So it fits, so which means that any combination of e to the power minus 8t and e to the power 3t is going to be a solution of this differential equation. But whether or not there exist some other solutions, we don't know yet. We just guessed that solutions of the form e to the power rt exist, and if this differential equation has a solution of the form e to the power rt, this happens if and only if r is satisfies the algebraic equation r squared plus 5r minus 24 equals 0, and there are just exactly two values of r that do that, which are minus 8 and 3. Well, and here is the definition, right? So this definition it kind of mimics the process that we just went through. So given a second order homogeneous linear ordinary differential equation with constant coefficients, this is very important, by the way. All these words are important. So it has to be homogeneous, so that the right hand side is 0. It has to be linear, so it has the right structure. It has to have constant coefficients, so this a, b, and c must be constant coefficients. Then its characteristic equation is the algebraic equation with the same constant coefficients. So we just take a, b, and c and form a quadratic equation with the same coefficients, and that quadratic equation is called the characteristic equation of the differential equation. So this example that I went through can be easily generalized. So, and what we have observed is that if r is a root of the characteristic equation, then the corresponding exponential function is a solution of the ordinary differential equation. All right. So if you maybe let me go through this one more time, because it is important. All right. So suppose that we substitute. Y equals e to the rt to the differential equation. So y prime is r e to the rt, and y double prime is r squared e to the rt. Then substituting this to the differential equation, we get a r squared e to the rt plus br e to the rt plus c e to the rt. And now we can factor out e to the rt, and the remaining part is a r squared plus br plus c, and this is 0, so this is 0. Okay, so if r is the root of the characteristic equation, then it gives us a solution of the corresponding differential equation. Well, but then the characteristic equation is a quadratic equation, and usually it has two roots. So, and if these two roots are real numbers, then what we have constructed is two solutions of the linear differential equation, and they well, they are in this exponential form. Well, however, we still don't know whether this formula covers all possible solutions of the differential equation. And the other thing that we don't know yet is what if the characteristic equation has a repeated root or complex roots. It may happen, right? So for example, what if the characteristic equation is r squared minus 10r plus 25 is 0. So when the left hand side is a complete square. So this is r minus 5 squared is 0. So 5 is a double root. Or if the characteristic equation is something like r squared plus 1 is 0. So then we have complex roots. What do we do then? What if the differential equation is not homogeneous? Again, if the right hand side is not 0 but some function of t. And finally, what happens if the differential equation, if the coefficients are not constant? So these are all very important questions, and what is going to happen is that first we are going to try to attempt the last important question, and based on our attempt to solve this, to consider differential equations with non-constant coefficients, we are going to develop a general theory. But that general theory can be actually used to completely answer important questions from 1 to 3. So although we will not be able to solve linear differential equations with non-constant coefficients, that's impossible, sorry, but the attempt to do it, it kind of provides other answers. Okay, so now please